We're now looking at just mixed problems involving non-right angled triangles. So we want to evaluate x. So again, what we've got to look at when we're not sure whether we've got the cosine rule or sine rule is what data have we been given and then what rule to put in place. Because we know it's either going to be the sine rule or cosine rule. So we've got two sides here, and we haven't got the included angle. We've got the two angles that are opposite them. So that should be a hint that if the angles between them is not there, then we have the cosine rule to play with. So we've got the two sides opposite the angle. So x on the sine of 63 degrees 18, 7.6 is opposite the 46 degrees 23 minutes. Again, multiply through to get x by itself, and then put that all on the calculator. It gives us the 9.4. So it's really a case of making sure we get the right rule depending on the data we're given. So this time we've got 93 degrees 45, we've got theta, and they're both opposite sides that are given. So again, sine rule there. So sine theta on the 5.4 and the sine of 93 degrees 45 minutes on 6.8. Again, we can put that in, multiply through by 5.4, get the expression there, calculate it, and take inverse sine, shift sine to do that, and we'll get an angle of 52 degrees 25 minutes, which sounds reasonable because it's less than 93 in that situation. So again, applying the sine rule because that's the data we're given. This time we're given two sides and we've got the angle between them. So that means we're going to have to use the cosine rule because we want to find n. So that's, if we got that, we apply the rule. So the 2.7 squared, 3.5 squared, 2 times the 2.7 times 3.5 times cosine of 102 degrees 34 minutes. If we put that into the calculator and then write it out, n squared is equal to that, and then take the square root. So 4.9 sounds reasonable. It's greater than 2.7 and 3.5. So it should be larger than those two sides because it's opposite, obviously, what's going to be the largest angle. And then the next part is find the area of the triangle. We've still got the two sides in the included angle. So half times the 3.5 times 2.7 times sine of 102 degrees 34 minutes. And that gives us an area of 4.61 meters squared. So again, we see what data we're given, we can apply the problems. Three sides here, and we need to find the angle. That means it can only be the cosine rule, because once we've got three sides and no angles to work with, then must be the cosine rule. So the 5.1 squared plus 5.3 squared minus the 8.7, because that's the one that's opposite the angle we need, over 2 times 5.1, 5.3. We get a negative. Remember, it's not a problem because it means it's going to be an obtuse angle, which makes sense because we're opposite the largest side in that problem. This time we've got Adrian, and he's doing some angles of elevation. So Adrian's at A here. He's got 25 degrees as an angle of elevation. Jane's at an angle of elevation of 30 degrees. And she's standing 10 meters closer. So that distance there is 10. So what we want to find is the length of BJ. So again, we've got to do a little bit of manipulation. So from our exterior angle of a triangle theorem, if that's 30, it must be equal to the opposite in some of the opposite interior angles, which means that angle there must be 5 degrees. So the 5 degrees is opposite the 10. You could also have said, well, that's going to be 150 plus 725 is 175, so that must be 5. So that's where we're going to get the sine 5 from, because we got two angles and a side to get BJ, the side BJ, which is opposite sine 25, and 10 is opposite sine of 5, so we multiply by sine 25 on both sides, and we're able to get BJ as 48.49. Now once we've got this side BJ there, we need to find the height of the tower. So we've got to find BC. So now if BJ is the 48.49 that we just calculated, and that's angle 30, we can go back to right angle triangle trigonometry. That first part, to get this side, we needed sine rule because that's where our data was. But now, because we've got the hypotenuse, the opposite, we can use the sine ratio. So keep in mind, as we've said before in class, keep thinking right angle triangles am I able to use that? Well, we have got a right angle, so we're able to go back and use that rule then. So sine 30 is equal to 40, BC on 48.49, multiply through by the 48.49, times the sine 30 and gives us 24.2, which sounds reasonable as well. This time we got a ship that sails 270 from Sydney. So there's our boat sailing at 0.055, so that's going to be an angle of 55 degrees. Turns and sails for 380 kilometres at 120, so it's 120 all the way around there, which means that would be an angle of 30 degrees there, because it goes on from 90. Remember, it's 90 degrees there, so 30 degrees around there. How far is the ship from Sydney to the nearest kilometre? So we want to find the distance there. We've got two sides there, and we want to find the third one. Have we got the included angle? Because we haven't got the angles there, but that's alternate. So 55, 55, that makes it an alternate angle to there. And because that was 30 degrees and 120 around to there, it's 120, 180 all the way around, so that gives us an angle of 60. So that's where we're going to get the angle of 115 degrees. The 55 plus the 60 allows us to get that included angle. We apply the cosine rule. Calculate it, we get x squared, and then take the square root, we get 551 as our angle there. So again, a lot of times the hardest part's going to be in the interpretation and just making sure we get the correct rule. This time we've got a regular pentagon, so all sides are the same, so all sides are 3, which makes life easy, or easier. And we want to find the size of the angle AFB. So AFB, well, we rely on our geometry now. So because it's 360 all the way around, and these are all the same because they're regular, because it's a regular pentagon. So we just divide it by 5 and gives us 72 degrees. Show the interior angle sum of a pentagon is 540. Well, if you remember our rule, that we could split a pentagon up into 3 triangles, and then multiply that by 180, gives us 540. So if you remember that rule, your angle sum, that's from junior geometry. And then find the length of AF to 1 decimal place. So we want to find the length here. So, well, if that's 3, that is going to be 72 degrees. I've done it using cosine rule. You could have done it using sine rule if you like. There's more than one way to do this, because I'm going to let that side, those sides are going to be equal as well. So if I take the two sides there and have x squared plus x squared, 2 times x, cosine of 72, which is the included angle, and that would be equal to the opposite angle squared. So that's where the 3 squared comes in. So I've applied the cosine rule, except I'm finding the two sides here. So I can still get an equation just in x squared. So x squared, 2x squared minus 2x squared cosine of 72, which I can factorize the 2x squared out of. And then if I divide the 9 by the cosine, 1 minus cosine of 72, well, I've divided both sides. That gives me approximately 13.002. Again, don't round it off yet. Divide by 2, and then take the square root. Then I'm able to get the 2.6 as my answer to my problem there, which sounds reasonable because 72. And the other way we could have done it, if that's 72 and this is isosceles, that's 36, and that's 36 as well. So you could have used the sine rule to calculate that as well. It's up to you. That's not a problem at all. You could also have dropped down a right angle, drop down a perpendicular bisector, use right angle triangle trigonometry to find that side as well. So there's more than one way to do that. I'd probably pick the hardest way to do it, but that's not a problem. It still worked out okay. So keep in mind what your problem's asking you to do. Being able to interpret the problem, that's going to be a big one. Being able to draw a diagram if one's not given to you is going to be important as well, because you have to be able to draw up and get the triangle that you need to manipulate. That's the big key. If you can't draw up the triangle, you're not going to be able to apply the trigonometry correctly to actually solve this. So you've got to be able to draw the triangle from the data you're given, and then deciding whether it's going to be the sine rule or cosine rule, because then you've got your data on your diagram and you can see what angles and what sides you've been given, and then making sure we calculate it correctly and and not making any simple errors as we go through. So there's different problems. You're going to face more of them. There's always ones going to come through, and you're going to have more of these sorts of ones later on in the course when we start dealing with radian measure. So this one can be applied in lots of different areas. These rules can be applied in lots of different areas of measurement.